who is going to talk about humidity profiles from GNSS radio occultations for observing atmospheric rivers and the influence of background data.
All right, thank you, Mr. Chairman. This talk is by Bahari Rahimi and myself. So Bahari would have liked to be here in person, but she is expecting a baby and cannot travel anymore. So probably you will see her in 2 years from now. Jennifer Haase has already given a nice introduction to atmospheric rivers. So here are just the main points. There are really important narrow regions responsible for lots of the water vapor transport in the exotropics and responsible for many extreme events. And here, just in terms of cloud cover, we see the typical example for a Pineapple Express bringing water vapor all the way from Hawaii to California and Oregon and so. When we represent atmospheric rivers, it's often done in terms of precipitable water vapor. And in order to do that, we need first the integrated water vapor. So we take the water vapor density and integrate it all the way from the surface to infinity. So infinity is less of a problem, but the surface can be a problem because there's lots of water vapor in the lowermost kilometers, and not all our profiles penetrate so far down. So we have to expect that we miss some of the integrated water vapor. And if we divide this by the density of liquid water, we get precipitable water which is given in millimeters. So either maps are shown in kilogram per meter square or in millimeters. And this is an example for the Atlantic Ocean. So here it's given in millimeters. So 35, 40 millimeters is a pretty high amount of water vapor. And this one is extended all the way from the Caribbean to United Kingdom, and then even further to Norway, and created havoc there. So here, for example, in UK, Ireland, it is known as Storm Desmond. In Norway, there was another name, Sinne, with lots of strong wind, rainfall, and so on. And so the question already some years ago was, can we observe atmospheric rivers with radio occultation? Of course, we know these are comparatively narrow streams, so our might not be the best choice to do it, right? On the other hand, we have the high vertical resolution, and this traditional passive microwave sounders, they just give the integrated content and no information about the vertical structure. And we have a good coverage over the oceans. And then another question is when we derive a water vapor from RO, we always need this background information in the 1D vars. And another question is, if we look at the specific humidity profiles, do they just contain the prior profile, or do we add additional information by the measurement itself? And of course, what I will not present in this talk here, we have to expect an underrepresentation of the integrated water vapor because of the profiles not reaching down to the ground. This is not covered here, but we have a paper in atmospheric measurement discussions, which is comparatively close to being published. This is something I've already presented at RWG7 a while ago. So in gridded RO data, we see, in this case, it's the same example, Desmond and Sinne. What we have seen there as well, so if you look at water vapor profiles, and here, this is averaged. So this is how it proceeds in time, right? So these are different days here, looking at certain grid points. We can see that these atmospheric rivers have quite different vertical structure. And of course, that's something you don't see in the integrated water vapor. So looking at the vertical structure might be interesting as well. And now just one measure. So I will use data from produced at Wegener Center and at UCAR. And one measure I will use is the retrieval to a priori error ratio, right? When we do the 1D var, we wait background and we weight data, and where we trust in the data, we weight the data more than the background. And this means on average, so if you look at this plot here in July, we can expect to get information from the data in this height range here. Further up, it's basically just the background we are seeing. So we don't expect any additional information from the data itself. And now here I show a few examples. I just focus on this here. So we have CDAC and Wegener Center specific humidity profiles. CDAC is always here in violet, and Wegener Center is in green here. And together with that, I have the background profile and the respective reference profiles that have been used. And here, this is an example here. It's an example, a pretty interesting one by itself, because this one brought enormous amounts of water vapor to Iceland, even further north. You would not expect 40 millimeters of water vapor there. And quite often, so here, if we look at this RIR measure here, this is the height. So in this area here, we would expect increments from the measurement itself. And if you look here, there's quite good agreement between everything, right? When it comes to the CDAC data, there's sort of a bit of a wave-like structure. I don't know, but could be. So this is pretty early in 2009. So maybe the background profile has been used with comparatively coarse height resolution, and I could imagine. I don't know, but that the background pulls the data to the solution to the background at these points. But I don't know, maybe Doug can tell more about this. I'm more interested in the result at the edge of the atmospheric rivers, in particular at the western edge. And in this case, we are looking at one. So this is Southern Africa. So this one has been hitting Southern Africa here. And here you see that I have two points here for the same profile. And this is related to the fact that the way how the reference point of the profile is computed is different at CDAC and at Wegener Center, right? At Wegener Center, we use the approach, we take the straight line connection between the two satellites, and if the straight line connection hits the surface, that's our definition of the reference point of the profile. This refers to an altitude of about 10 to 15 kilometers. Worked very well for when we specifically looked at temperature change in the stratosphere, in the upper troposphere. But if you look at the lower troposphere, this means that the UCA definition, I think it's still the one that if the L1 excess path reaches 100 meter or so, and then, or at least back then, so it corresponds to a height of maybe 3 to 4 kilometers. But this also means, also the computation of the tangent point trajectory. So at least in this OPS 5.6 retrieval, so it's more realistic at UCA, right? So this path in the lowermost 14 kilometers is longer. For our application here, it means we have, so it's always the same profile, right? Different interpretations of the same profile. That means we are extracting the background profile at different locations. And this can serve as an unplanned experiment, if you want. What does the retrieval, if we start with totally different backgrounds, and because there are such sharp gradients, in this example, for example, the CDAC background has been taken at a very at a drier location than the Wegener Center background. And what comes out here, so if we look specifically at this height area, so it seems that, so at least the explanation would be consistent with that. The CDAC background was already pretty dry, and apparently the atmosphere was even drier, so within the limits of the 1 dvar. So the CDAC result is is very dry here, right? So that's this line here. Wegener Center started very humid, and even though the 1D solution tried to bring it to dry conditions, but could not all the way go to the CDAC solution because it's confined by the limits set within the one. Another nice example is this one. So here again we have. So this is the reference point of Wegener Center. This is the one of CDAC. So the Wegener Center again in a very humid area, and we see this here. So that this yellow line. So the Wegener Center background is way more humid than the CDAC background. Nevertheless, the results converge very well to a almost common answer. So even if we have very different background in the area where we allow the information of the measurements to have a certain effect, there seems to come to quite a common agreement. And this would be my summary. So there is, to answer the question, so there's clearly information in the RO-derived profiles that has not yet been in the background profile, at least in the part where the 1D scheme allows it. And even starting with very different backgrounds, the two retrieval schemes try to come to a common answer, if possible. What I've not shown here, or what I've not mentioned, in addition to the ECMWF short-term forecasts Wegener Center uses as background, I've also shown the ECMWF forecasts, and in general, there's very little change between the short-term forecast and the analysis, and this means we use the short-term forecasts as a background and the analysis as reference, right? And in general, there's very little difference between the two, though, because the ECMWF at least does essentially not use the water vapor information in the data. What's also important, the tension point trajectory matters. We have seen that, and so it seems to be attractive to come, since the analysis don't use the water vapor information at all, right? It seems to be attractive to produce a view at the 3D structures of atmospheric rivers by combining the SSMI data with very good horizontal resolution and the RO data with very high vertical resolution, taking all that what we have here into account. And of course, there are areas, what Jennifer has been showing, in areas where you have airborne radio occultation data, drop zones, and airplane measurements in general. You might not need that, but there are atmospheric rivers in other parts of the world where we don't have that many measurements. And that's it from my side.
Thank you, Uli. This was a very nice presentation. And we have time for one quick question. Yeah.
Yeah, Uli, this is very interesting for application for the specific atmospheric condition. And we just actually 1 year ago published a paper, and then we kind of quantify the difficult part for this using atmosphere humidity data from RO. Actually is because the reflectivity itself, the sensitivity to water vapor is location dependent. So when it's the weather, the weight to background is less. Okay, so it's drier. When it's drier, then it's the weighting will go to the background. So at a very dry region, you actually will depend on your background. I'm talking about temperature and water vapor too. So I think this is a little bit difficult to using one of the reasons to using so-called 1D derived humidity to do the climate research. But it may be not so bad for this atmosphere vertical variation type of detection, like an atmosphere river. So this is my comment.
All right. Yeah, I think we have solved some of the easy problems, and we left some of the more difficult ones, and those are up for the young generation to take over right now.
Any other questions? Maybe a quick one.
So thank you. It's very good to see this application, and it's also good to see that you're optimistic. And I think we can be even more optimistic. So you're using error covariance matrices from ROPP6,
Yeah.
and at the moment we are working on some improved error covariances, and they seem to be able to improve the performance,
Okay.
especially at mid latitudes. Also in cases where we have low specific humidity. So this is all very encouraging. Yeah, this may be just an information. I also say that we
it's-
should
yeah.
wait until we have gone through the review process with
Yeah.
these, but they will come up in ROPP.
Okay, that's good. And I might also add, so we use the old retrieval system of Wegener Center. With the new retrieval system, we expect even better results, of course.
And Stephen, do you have a question?
So Uli, I haven't read the previous work, but do we actually have a complication here from super refraction?
Of course, right. So I've focused more on the part between, let's say, 3-6 kilometers, where we have probably less of this problem, and where there's clear and clear increment between the background and data. There are lots of problems, but we are here to solve them.
Thank you, Uli. And I would like to invite Rob Krzyzewski, our last speaker for this session. And he's going to talk about atmospheric structures observed in the lower troposphere